In our last lecture, we left off with the idea of tristate. So, as we discussed in class, a tristate is actually a third state, and that allows us to define not only logic 0 and 1, but also a third state, Z, which is called a high Z, Z standing for impedance, which you can think of as being a high resistance. And so, under tristate, effectively, a circuit is now deciding, I'm no longer going to drive something to a logic 1, I'm no longer going to drive something to a logic 0. I'm effectively going to detach myself from the circuit, at least temporarily. And in that way, it can get out of the way of other devices. This is effectively what's happening inside of a multiplexer when you are detaching from all of the paths that are not chosen. So as we discussed in lecture, a good example of that would be in your stereo system. So if you had multiple sources for your stereo system, let's say you had an FM radio, an AM radio, a CD player, perhaps Bluetooth to connect to some wireless devices, an auxiliary line in, multiple different inputs, and you were choosing different ones as the source to go to your speaker, you would only want one of those sources connected at a time. And so the best way to get those other signals out of the way is to remove the signals you're not interested in. So if you decide you want to listen to the FM radio, you ought to disconnect from your CD player, from the AM radio module, from all of these other sources. Just get them out of the way and only allow the FM to come through. So one way that can be implemented is with the idea of a buffer. So the buffers that we have seen before just go through A, goes right on through, and goes out to C. Whatever comes in on A goes out onto C. But with a tri-state buffer, now B basically becomes the gatekeeper to determine if A is even directly connected to C. So you can think about that as being like this. Here we have this buffer, and A is coming through, and if it's connected, the same signal A will come out here, and it will flow on over to C. But B is deciding whether we're even going to connect this at all, so B could lift the gate, and it would do that under this circumstance when B is equal to a 0, or it could push this closed, push the switch closed, and complete a path from A through the buffer all the way to C. And so B is basically allowing us to open circuit or to short that particular path. So why would we want to do that? Really, it's if you want to connect two different outputs together. So if you want to choose one output at a time or the other one, if you have both of them, just as we illustrated in class, one trying to drive something to a 0 while the other is trying to drive something to a 1, you can result in a logical contradiction. And really, instead of getting a good clean 5 volt or so signal for logic 1, 0 volts for logic 0, or in other systems, whatever your voltage is defined as logic high, you can get an indeterminate voltage. And so in that case, you may not know if the output is supposed to be a 1 or a 0. So that allows us to cut off those particular inputs from that circuit. So here are some other buffer implementations. This is the buffer we just discussed. So if B is a 0, that's disconnecting, and so your output C will be this Z, or high impedance state. Otherwise, your output when B is a 1 will simply follow whatever A is coming through. So A being a 0, C goes to 0. A being a 1, C goes to 1. Right here, this is an inverter, so normally A would come in and the opposite of A would go out to C, but now the B input is acting as that tri-state buffer to determine if this is connected or not. And so here again, if B is a 0, it's not connected, high state, and otherwise the opposite of A comes out onto C, as you see right there. Here is basically the same idea. These two buffers on the right are very similar to what you see. This one non-inverting and this one inverting, but the difference is you notice the little bubble right there. And so effectively B is acting exactly the opposite way of what it did before. So the little bubble just means opposite or complement. So in this case, when B is a 0, that's when A flows through to C. In this case, when B is a 0, that's when the complement of A flows through to C. So this is one way that we can represent a 2-to-1 multiplexer using a couple different tri-state buffers. So in this case, our B is going to be our select line, the same thing as what you have down here. In this case, we have a buffer that's active when you have a logic 1, and in this case you have a buffer that's active when you have a logic 0. And since they're complementary, D will only have A or C. It can never have a conflict where both are coming through. One of them will always be in a high impedance state, and the other one will always be driving the output to the D line right here. So in this case, this would only really work if you had two lines or two inputs competing for the same line space. A decoder is a way to drive exactly one output high based upon a binary input. Or you can have an inverted decoder which would drive exactly one output low. So in this case we have a 3 to 8 line decoder, and depending upon what binary value you put in here, one of these lines will be active with a 1. All of the others will be a 0. So if you happen to put in 0, 0, 0, then Y0 will turn on and be 1. That's what you see here in the top row of the truth table. If you put in 0, 0, 1, Y1 is active, and you see that all the way through. Depending upon what you put into A, B, and C, then that particular line is active. So this is a decoder, and that can allow us to basically choose which of the tri-state buffers we have on. So we can have each of these decoder lines determining which of our inputs are coming through. So that's one way we could actually build a multiplexer, is using a decoder and several different tri-state buffers. Decoders are also used to extend memory. So this way you can determine which memory chip is active if you had multiple memory modules. This way you could choose this to be part of the address bits that you would have. So part of the address bits that you're addressing in memory would be A, B, and C. And then this could choose which of those memory modules are active. That was actually part of a project that I did when I was an undergraduate in our microprocessors class at Virginia Tech. We actually had to wire up our own external ROM chip, and in that case we needed to have extra addressing capabilities, and so we sent some address bits to inputs on a decoder, and then the outputs determined whether they were selecting internal memory or external memory that we wired up. This is an inverted decoder. This is actually a 4 to 10, so you might think about only having values between 0 and binary for 9. So this could be basically a binary coded decimal input. And in this case, these are inverted outputs. So only one of them will go low, all the rest of them will go high. So here is the truth table for the 4 to 10 decoder. So in this case, if you have 0, 0, 0, 0, the output on 0 would be a 0 all the way up through. If you actually put something bigger than 9, then you wouldn't have a 0 anywhere. So in this case, 1, 0, 1, 0 would not activate any of your outputs and making them logic low. This is good if you're trying to choose some things that are active low. So if you had a buffer, a tri-state buffer where the B had the bubble input on it, so it was activated when it was the opposite logic, in that case you might want a decoder to work this particular way. So you can actually realize a min-term expansion using a decoder. So in this case, you can actually choose which of your min-terms you want in a function, and you can put them together. In this case, this is an inverted decoder where the output is logic 0. And so you'll notice if you have something like this, if you put a NAND gate with each of these inverted outputs here, that's effectively like putting a bubble on the input right here, which basically is taking this and making this like a NOR gate, and then if you invert the output it makes it like an OR. So effectively what's happening when you choose the appropriate min-term, let's say example min-term 1, you would put in 0, 0, 0, 1 into A, B, C, and D, and then the active line would be this line 1 right here. And so that would be a 0. All the rest of these would be a logic 1. And so because we don't have all 1s here, then the output is a 1. If you had all 1s here, that would mean that you're not selecting any of the min-terms that are of interest, and the output here would go to 0. So you can actually use a 4 to 10 line inverted decoder and some NAND gates in order to realize your function. If you had a 4 to 10 line decoder that had non-inverted outputs, what you could effectively do is just use OR gates over here, and it would work the same exact way. An encoder is effectively the opposite of a decoder. So in this case, you activate one line, and then you get the corresponding binary code out. And in this case, D is indicating that you have at least one line active. So if you have all zeros, that means none of the lines were active. And so your output would be 0, 0, 0, 0, and you'd have a D there that would indicate that none of the inputs were active. You're also going to be looking for which of the inputs, in case you have multiple ones put in there, you're going to be looking for the highest input that is selected. So in this case, if Y7 is selected, all the rest of them are don't cares. You don't care if you also have a 1 on Y0 or Y1 or any of those things. Y7, since it's the highest, takes precedence, and you will get a 7 out. And of course, they're binary for 7, 1, 1, 1. And then your D will also be high to indicate that. If line 7 is not active and line 6 is, again, you don't care about anything less than 6, you'll get 1, 1, 0 for your output, and it follows all the way down through Y0 being the least priority. Adders are also very important. So if you wanted to develop some logic for adding two different bits together, you might want to think about how you could go about doing that. So if you look at adding A and B, you think about what the possible sums are. Well, if you had 0 and 0, of course the sum would be 0. We could represent that with as few as 1 bits. 0 plus 1. That also could work with just 1 bit. 1 plus 0 could also work with just 1 bit. But because 1 plus 1 is a possibility for 2 bits, we actually need 2 different bits for our sum. So in this case, the sum would obviously be 2. And so there's 3 possible outputs for the sum of 2 individual bits. So we could say in our truth table here, for A and B, the output would be X and Y, which X would be our most significant bit, and Y would be our least significant bit. This would be a truth table for a 2-bit adder. So let's expand that. Now let's think about if we wanted to add 2 different 2-bit values together. How many inputs would we need? Well, if each of the values being added together are 2 bits, you'd need a total of 4 input bits. Then how many outputs would we need? Well, we'd have to think about what are the possible values of the sums of 2 bits. Well, if those 2-bit values were added together, what's the smallest possible value we could get? Again, both of them could be 0, 0. So the smallest possible sum would be 0, so that can be represented with just 1 bit. But let's think about our maximum scenario. The largest value we can represent with 2 bits is 1, 1, which is binary for 3. And so if we added 3 plus 3, the value we would get is 6. And how many bits does it take to represent 6? Well, 6 is 1, 1, 0, so that would take 3 bits. So we would have to have a 3-bit output in that case. And then the question is this function incompletely specified? Well, it does have a possibility for every possible input, but with 3-bit output, it is not possible to achieve an output of 7 if our logic is defining that. So if we had that driving another circuit later on, then that 7 would be a don't care. So on our output, it's just never possible to achieve 7. So it's not truly incompletely specified because we do have a deterministic solution for every possible sum, but one particular output value is unreachable. So that's what I mean right here. If you were to take the output from that, so that sum value, which could range from 0 to 6, and drive another circuit, it would not be possible to achieve all those combinations because 7 would be left out. So here's our block diagram for such a 2-bit adder. Over here we'd have number n1, which would be represented by the 2 bits going into A and B. Then we'd have number n2 going into the 2 bits for C and D. And then we'd have x, y, and z as our sum over here for n3. That would give us a 3-bit binary sum. And so if we did all our possible combinations here, we'd have 2 bits for n1, 2 bits for n2. Here are all the possible combinations, and then we're actually extending that over into a second column over here, just so it would fit on the slide. So as you see, with 2 2-bit values being added together, we've got 16 possible combinations happening here. We can simplify that a little bit and showcase this as a nice 4-bit adder. So in this case, not sure why my slide keeps trying to advance. So in this case, we could write a 4-bit adder with 8 such inputs down here. So we could have our least significant bits for A and all the way up through our most significant bit for A, least significant bit for another number B up through most significant bit for another number B. And then in this case, our sum would require up to 4 bits. So with a 4-bit input, we actually might also have a carry out here. So if you think about adding 2 4-bit values together, the largest possible value we can get for each individual 4 bits would be 1, 1, 1, 1, which would be 8 plus 4 plus 2 plus 1, or 15. And so the largest possible sum we could get would be 30, 15 plus 15, and 30 would actually require 5 bits to represent. So in that case, since we like to keep the same number of bits, we could really write this as 4-bit input, 4-bit output, and then if our sum was greater than that, we could actually call that a carry out, and then that could also be used to drive into a carry in. So if we were to put this in parallel and put it with another 4 bits, we could actually put these side by side to make an 8-bit adder and tie the carry out here, C4, into the carry in, C0. So we could actually carry values in and then carry values out. If you were to do the comprehensive truth table for this, now we have 9 inputs. And so the truth table would have 2 to the 9 rows. How many is that? 512. So you would actually have 512 input combinations, and you would have to realize the output for all 5 outputs 512 times. As you can see, just by adding small values, this becomes rather tedious. So there's bound to be a better way to do this. Well, really, the logic for an adder is the same for each of these bits. As you know, algorithmically, when you first learn to add, you take a value, you add it to another value, you figure out the ones place, and then there might be a tens place that needs to be carried out. And so we can do the same thing for a generic number of n bits. So if we were to just continue this, every time we add a bit, we double the size of our truth table. And so our logic becomes twice as complicated. We don't want to continue doing that. We want a generalized approach. And so, as I was just mentioning, if we have 1-bit adders with a carry out and a carry in, that is called a full adder. If we don't have the carry in, that's just called a half adder, but you won't see very many of those. Every time we look at each place where we're adding values together, we're going to look at 1 bit, add it to another bit, and consider whether there was a carry in from the previous 2 bits being added together. And then we can immediately figure out whether the sum will be a 1 or 0, and then whether there'll be a carry out over to the next column. So here's an example here. If I were to add these 2 values together and I had a carry in, let's suppose our initial carry in is going to be 0. So if we add 0, 1, and 1, that gives us a sum of 2. And so 2 is 1, 0, so we put down 0, that's in our least significant place, and then we put our 1 over here as the carry out. So 1, 0 is binary for 2. Now we take this as a carry in and add that to these 2 ones. 1 plus 1 plus 1 is 3. The binary for that is 1, 1. So we put our least significant 1 up here as the sum. and then we put this 1 over here as the carry out. Then we take this carry and add it to these two zeros here. 1 plus 0 is 1 with a carry of 0. So we put down our 1, we put a carry of 0 over here, and then we have 0 plus 1 plus 1. That's going to give us a 0 here, and finally we would have a carry out, which could go on to another adder if we had another bit, but if we didn't, that might just indicate an overflow. So inside of a lot of microcontrollers, you have an overflow bit that indicates that you added to a value that was bigger than what could be represented. In this case, we can only represent a 4-bit sum. We have 4-bit architecture here. So if this sum were supposed to be a 1, then that value would be too large. In this case, you can actually tie your carry out into your carry in if you wanted to form the 1's complement of that particular value. So that's one way we can do that. The truth table for the full adder. Let's go ahead and see if we understand this. If you had 0 plus a carry in of 0, what would be your carry out and what would be your sum? Well, the total there is 0, so both our carry out and our sum would also be 0. Now if we add 0 plus a carry in of 1, now our total is 1, so we'd put that in our sum, and we would have no carry out. Really, we're only going to have a carry out if our sum is 2 or greater. And so if we keep going, 0 plus 1 plus 0 gives us a sum of 1, same output, no carry. And then 0 plus 1 plus 1. Now our total is 2, so in this case we're going to write a 0 for our sum bit, and then a 1 for our carry out. So we're writing this where sum is going to be the least significant bit of our total, and C out is going to be the greatest significant bit, or most significant bit. So in this case, 1 plus 0, total of 1, so we get 0, 1. 1 plus 0 plus 1, total of 2, so we get a carry out, and 0 for the sum. 1 plus 0, in that case, a total of 2, so we write that as 1, 0. And finally, this is the only case where we have both a carry out and a sum. We have 1 plus 1, so that gives us both 1s for the carry and the total sum. If we were to write the logic here, the carry out happens whenever we have at least 2 of the inputs. That could be the 2 bits being added, or if we have a bit being added and the carry in. So if we have any of these combinations where you have at least 2 bits being added, you will have a carry out, because that means the sum is 2 or greater. In this case, the sum bit is actually happening whenever the total sum is odd, because that's when we see a 1 in our least significant digit. And this is an exclusive OR gate, which we've largely only thought of when it has 2 inputs. But actually what happens is when you have more than 2 inputs to an exclusive OR, it becomes an odd detector. And so if you have an odd number of 1s coming in on this, then your sum will be a 1. So that's the way that you can implement the full adder using the logic gate building blocks that you already know. How can we use an adder to subtract? So you can build a subtractor, and that really relies upon some of the numeric systems that we learned before. In effect, if you take a positive value, or any value really, and you add the 2's complement of a value, you have effectively subtracted. So we use 2's complement. Remember, 2's complement is found by taking a binary value, inverting all of the bits, and then adding 1. So in this case, positive values can be represented just the same as unsigned binary. Negative numbers in 2's complement we found by flipping all the bits and adding 1. So we can use those NOT gates and a carry in of 1 to make the 2's complement. So here we're trying to do A minus some value of B. So our A value is coming into the full adder just the same. And then our B value, we're converting to the 1's complement here by doing the inversion of all the bits. And then we are converting from the 1's complement to the 2's complement by having this carry in of 1 over here. And so that ultimately will give us the value A minus B, assuming that both A and B are positive integers.